No,
Yes.
looks good.
Okay, thank you very much. So I wasn't able to see kind of everybody in the network session. This is my first Volta Foundation. So appreciate your patience with me as I work through this, and want to thank you very much for participating today. So I'm going to talk about how to look inside your lithium-ion battery with a scanning electron microscope. And my idea was to just show a lot of examples of how people in the industry are using microscopes, from very basic benchtop system to air isolation workflows, and even operando experiments where we're can look at kind of real-time behavior of an electrode during charging and discharging cycling. So that's kind of the theme of my talk. And let's see if I can get us started here. So for those of you who don't know about Joel, we're a world leader in the manufacture of scientific equipment, and we cover a broad range of industry, from medical biochemical analyzers, industrial equipment, to analytical instruments. So we're proud to be celebrating our 75th year, and Joel has technical centers across the globe. I work for Joel USA, which supports all of the Americas. This includes Mexico and Brazil, and we even have offices in Canada. So our mission at Joel is to empower the scientific community like you by delivering outstanding technology and superior support while maintaining a kind of a leadership position in the industries and the institutions we serve. All right. So we make a lot of different types of products that might be relative to battery characterization. These include TEM for nano and atomic scale observation, SEM, EPMA, and OJ equipment for surface morphology, from the micro to the nano scale. Different types of detectors for elemental analysis, benchtop X-ray fluorescence, and then detectors that fit on our SEM and EPMAs, such as EDS, WDS, and something unique to Joel called our soft X-ray emission spectrometer, or SXES for short. And what's unique about this detector is that we not only get insights into the elemental composition, but also can get insights into chemical state. We make a variety of sample preparation equipment that's useful in battery research, from focused ion beam instruments, FIB-SEM, to broad argon ion milling, which we call our cross-section polisher for sample preparation. We manufacture NMRs, which are great for structural analysis. And in the battery industry, we can get insight into lithium diffusion, and mass spectrometers for chemical analysis and Gauss analysis, right? So today's agenda, again, we're going to focus on how we use SEM in the study of battery systems from the macro to the nano scale. I'll introduce our cross-section preparation tools. Predominantly the broad argon ion milling is very useful for preparing cross-sections for examination in a scanning electron microscope. For those who work with air-sensitive samples, I'm going to show some examples of our air isolation workflow. And I'm going to introduce two detectors that we can couple with our SEMs that can even detect the lithium. And I'll lastly present that case study where we do an in situ operando experiment, right? So why SEM? It always fascinates me that looking at materials at the micro and nano scale can give insights into the performance and behavior of your end product. So SEM is used in all aspects of battery manufacture, from the raw material characterization, quality control, failure analysis, reverse engineering or forensics. And beyond just morphological information, size and shape, we take advantage of the different detectors to provide chemical information, essentially creating kind of a nano lab within our SEM, right? So what can we look at in terms of battery systems? For the most part, any of the solid state components, starting with raw materials, the electrodes, current collectors, separator materials, and in the case of solid state batteries, we can even look at the electrolyte. The different kinds of information that we can gather, again, size and shape, right down to the submicron or nanometer scale. We can couple our SEMs again with these elemental analysis detectors so we can get composition, distribution of components, identify foreign materials that might affect the behavior, and even get some insights into the chemical state. So Joel makes a very comprehensive lineup of SEMs that cover really all the major applications from the macro to nano scale. We manufacture easy benchtop systems to ultra high resolution field emission instruments, and they all have their role to play in battery characterization. Operating any of these SEMs has never been easier. We have guided workflows that walk you step by step from sample introduction to image formation. There's embedded EDS detectors and a lot of quality and life improvements that help you get to the results quickly. We offer real-time element identification with our EDS. We can couple with anybody's X-ray detector, but we also make our own, which are fully embedded in the SEM, so that you can get kind of a real-time view of the elemental composition or distribution with live spectra or mapping. And our SEMs also have built-in no-code automation routines for those labs that need high throughput, right? So let's start. Here's a quick example of some battery data that was acquired with Joel's benchtop SEM. It's incredibly easy to use, these benchtop systems. They come at a great price point, and they become quite useful for battery characterization. The top image that you see is an example of anode material analyzed with our benchtop SEM. It was acquired with secondary electron detector at low voltage, and this highlights really the fine surface structure and coverage of the particles that make up this electrode. Below that image, we can see a backscatter electron image that's represented of a cross-section of a cathode. And this cross-section, what we're seeing with backscatter detector, and this benchtop SEM comes with both secondary and backscatter. Backscatter is great for compositional contrast. So what you can tell is different compositions based on the grayscale level. And what we're highlighting here is a contrast between the cathode material and the current collector. And our benchtop systems can even be equipped with Joel's EDS detector for elemental analysis. And to the right of the cathode image, we see an overlay of X-ray intensity maps on the backscatter image so that you can really see the elemental distribution across this cross-section. Particle shape and size can impact manufacturability and performance, and SEM is a great tool for this kind of study. We can characterize shape by a variety of metrics and show the distribution of that size or whatever shape metric that we want to, and get insight even on porosity. For high throughput labs, we can automate the image collection and batch process these images for this size distribution. If we want to take it one step further beyond particle size and shape, we can fully automate this process and not only get the shape, but classify the particles by composition. So one failure mechanism in battery systems would be thermal runaway reactions due to a short maybe induced by foreign particles or defect in the separator. It's an extreme example and it doesn't happen very often, but it's important to avoid situations like that, right? So many automotive manufacturers have adopted the automotive cleanliness standard VDA 19.2, which originated in Germany for looking at cleanliness in the production line. SEM is a great tool for implementing the measurement in this standard because not only can particles be detected down to the submicron scale, but chemical composition can be determined using our EDS elemental analyzer. Particles can be classified by chemical type, where the sediment is collected along the manufacturing line on filters. With Joel's particle contamination inspection system, multiple samples can be placed in the SEM. We use the backscatter detector to threshold the particles based on their grayscale. And by detecting these particles, we can go back and analyze these automatically to get elemental composition. And recipes can be created for kind of a quick and easy workflow, and the entire process can be fully automated within your lab. Another useful automation function in SEMs is larger area montage. This comes standard with all of our SEMs, this ability to automate image collection and basically create a mosaic, stitch those images together. And not only can we automatically acquire images, we can do that from multiple detectors and actually collect montage maps and stitch all of that data to find a composite final image. So on the left here, we see kind of our data management software. And in this example, I'm showing kind of a 4x4 tiled frame montage. So we have a total of 16 frames. The whole montage was collected with both backscatter, secondary electron images, and X-ray intensity maps at each tile. And the entire process took about 25 minutes. On the right, I'm showing the composite image from those 16 tiles of the backscatter electron image, as well as an overlay of the carbon and oxygen maps. This shows a screenshot from one tile as it was being collected. Since our EDS detector is fully embedded, we get a real-time display of that elemental composition as we're collecting the data. So you get instant feedback of the composition of your material as you're doing this analysis. And finally, here is an EDS map of one of those tiles, just to show an example. This was a medium pixel resolution image of 512 by 384 pixel data with one frame. It took about 40 seconds to collect at 5 nanoamps. So you can see we get quite a good resolution and good signal to noise. So we can collect this data in a fairly short time. Moving on to another example, when you want submicron characterization of materials, if you really need to look at things at very small scales, field emission microscopes are an ideal choice. So this is showing examples of graphite images. These were collected at 100,000 times magnification at very low voltages. This is a comparison of a conventional field emission microscope image on the left versus ultra high resolution, or kind of our flagship field emission microscope on the right. With these ultra high resolution instruments, we're capable of ultra high, low voltages. We are using in-column detectors, which give us great resolving power. So you can see the difference in how sharp the images is, and we can really see the layering in that graphite particle, really at the nanometer scale. So lower voltages also means more surface structure can be observed. And that is really readily apparent if we look at the surface up here. This is another example of the type of information that can be gleaned kind of with these field emission microscopes. When we use these in-column detectors, one of our detectors has an energy filter. And by varying the voltage of that filter grid, we can kind of select the energy range of the electrons being detected. And that helps us get different kinds of information about the sample. So applying a negative voltage, we get, we're kind of repelling any of the low energy electrons. So what you see on the left-hand side here is something with more compositional contrast. So the gray scales are showing us kind of what's different chemically within the material. We need our EDS detector to tell us what, but at least we can say we see differences in the chemical composition. Applying, going the other way, applying a positive voltage, now we're collecting more of those low energy electrons. This is giving us much more surface detail or surface characterization. Okay. Using that same detector, here's some examples of battery separator materials. Again, the power of these in-lens detectors is the ability to work at these ultra low voltages and really see fine surface morphology of the material. So in these images here, you can see that's a 50 nanometer scale bar, so we're quite high magnification, and we're getting really the ability to see kind of crystalline morphology within the polymer. And we need to be at these low voltages because separating material, it tends to be very thermally sensitive. So it's susceptible to beam damage just from imaging. If we use higher voltages, we might break these fine, thin tendrils, or may even make the pores expand as the material kind of degrades. And that would mask what the true structure of the separator material really is. So next I want to discuss some low voltage analysis, or kind of keep within that theme. What we're seeing here is an electrode image that was collected at 4 different voltages: 5 kV, 2 kV, 1 kV, and 500 volts. And if we focus just on the 2 kV and 1 kV images, you can clearly see that there are 2 different types of grayscale compositions, even texture here, a darker gray and a lighter gray that's sitting on these particles. It's not really as apparent in the 5 kV image because our penetration, the X-ray, the electron beam penetration depth is too deep, and we're looking too much subsurface. So by lowering that voltage, we're seeing or detecting more of the surface and the materials on the surface of these particles. And so we're getting an idea that we have 2 different compositions here. So the next question is, well, at these low voltages, if we can see it, can we analyze it and get an idea of what the chemical differences are between those 2 particles, or the grayscale values? And the answer is yes, as long as you are interested in elements which have X-ray lines that can be excited at those low voltages. And I guess spoiler alert is yes, you can. So let me show you an example. This is that same image where we collected X-ray data. This data was collected at 1.2 kV and 6 nanoamps. So another advantage of field emission microscopes is their ability to deliver very large probe currents under high resolution conditions at low voltage for efficient analytical characterization. So if you look at this map data, you can see that the lighter gray areas are more rich in fluorine. The lower left here, you can see the fluorine X-ray intensity map. And the darker gray areas are more rich in carbon. One of the benefits, again, of doing this low voltage analysis is that our penetration depth is very small. So the mapping is going to be more representative of the composition that is on the surface, and that's readily apparent here. We can see differentiate the fluorine-rich and carbon-rich areas. The lighter elements will also be detected more accurately since the X-rays have less chance to be absorbed within the material. And this low voltage analysis also allows us for better analytical spatial resolution. Switching gears a little bit here, some components within a lithium-ion battery system can be very air sensitive and require special handling. So Joel offers a complete air isolation workflow across our product line. For our benchtop systems, we partner with Zonexus company. for the air isolation piece. That's that little sample holder that you see here. And then for the remainder of our products, from tungsten SEM to the ultra high resolution field emission, we make our own transfer systems. And what's nice about these transfer systems, they're not only compatible with the SEM, but they're also compatible with our sample preparation tools for cross-section for very easy, seamless transfer from preparation, glove box to preparation to SEM analysis. And so the remainder of my talk, I'd like to introduce some examples of our air isolation workflow where I'm going to incorporate these preparation cross-section tools and also introduce some of the unique X-ray detectors that we use for lithium analysis. But quickly, this is kind of an example of why air isolation transfer can be important with some systems. So this is a lithium cobalt oxide particles or images of that. On the right-hand side, you can see this has been exposed to air, and on the left, this has not been exposed to air. So it's with an air exposed sample, even just briefly, you can see deposits here. There's an expanded view right here on the surface of the material formed because of rapid oxidation. And so this oxidation will mask the true surface structure. So you're not really seeing the true nature of what your particles look like. So I'm going to show a little video here in a second here with a typical air isolation workflow from our using our cross-section polisher to create a cross-section to SEM analysis. And the benefit of using this cross-section polisher, it's a broad argon ion milling tool, is that it eliminates artifacts associated with a traditional mechanical preparation. So pristine cross-sections can be made from difficult materials that are brittle, fragile, multi-layer coatings that might have differences with thermal expansion. And it can also be equipped as a cooling cross-section polisher for cryogenic temperatures, which is beneficial for thermally sensitive samples that might degrade otherwise if you expose them from the argon ion beam. So let me just start this. The sample is mounted in our transfer vessel in a glove box and then brought to the cross-section polisher. Once the chamber in the cross-section polisher is fully evacuated, we can open the cap. The cross-section is then made by exposing the sample to the argon beam. Here's an exploded view here of the shielding plate that masks the sample. So only the area that's protruding from that shielding plate is milled away. So the width of the cut is typically about 1 millimeter, and the depth will be dependent on the milling time. The specimen stage was rocking, and that minimizes any curtaining effects for a nice smooth cross-section. And on completion, the cap is placed back on, and this transfer vessel is brought to the SEM to continue with your imaging or analysis, right? I'd like to also introduce, for the next examples, the 2 types of X-ray detectors that are available with our ultra high resolution field emission microscopes or even EPMA instruments that allow for the detection of lithium. The first one is GatherX, which is a windowless ADS detector. It's a spectrometer that is ideal for light element detection. And it's possible to detect down to lithium in the right oxidation state. It's very fast and easy to use as any EDS detector. And we can work at very short working distances too for very high spatial resolution so that we can, really it's versatile for many, many different types of applications. The second detector I want to show you some examples from is our soft X-ray emission spectrometer. This is very unique to Joel, and it measures low energy X-rays in the soft X-ray region. There are many resonance in this region, and with this detector's very high energy resolution, it's like 0.3 eV at the aluminum Fermi edge, and the high peak to background, we get very high sensitivity. So we can reach detection limits in many instances down to about 100 parts per million. And it can provide not only elemental information, but also insight into chemical state. So let me describe these a little further. The GatherX windowless X-ray detector, so windowless, so more efficient collection of the low energy X-rays, right down to lithium, is great advantage. But it can perform analysis at any kV with very high sensitivity, and it's especially suited to the low voltage analysis for high spatial resolution microanalysis. It has kind of a racetrack design, which ensures very high collection efficiency of our X-rays, and also allows us to get up to very close working distance for very high magnification analysis. So we can really do X-ray collection as close as 1 millimeter. And here's an example of a material of map data collected with our GatherX. This was a cross-section of a silicon anode of an all-solid state lithium-ion battery material. And we can see the X-ray intensity maps, the lithium in yellow, the silicon in cyan, and we can detect and deconvolute these low energy X-ray lines with very good resolution. And it's pretty amazing since the silicon K and the lithium L lines are only about 36 eV apart. Okay. That second soft X-ray emission spectrometer, there are 2 versions of it. Low energy range, optimized for light element analysis, is perfect for battery applications. There's also an extended range system that is more optimized for transition metal chemical state. Looking at the schematic here on the left, the system works by using a focusing mirror to collect the X-rays on a diffraction grating where the wavelengths are separated and detected with an X-ray CCD camera. And the spectrum are displayed much in the same way as an EDS spectrum. Right? As I mentioned before, because of this very high energy resolution and high peak to background levels, we get very high resolving power that allows spectral acquisition, even in the valence band, to be observed. And this is where we get that, insight into chemical state differences between compounds or crystalline versus amorphous materials. So here I'm showing an example of silicon, crystalline silicon versus a spectrum of amorphous silicon. So peak position and peak shape changes help us get an understanding of amorphous versus crystalline material, or some kind of combination of the two. Here are another couple of examples of soft X-ray spectra where you can see differences in spectrum shape. Between lithium metal and lithium sulfide here, you not only see difference in the shape, but you can also see kind of a shift in the lithium line, which is giving us kind of some kind of indication that we're getting alloying or bonding. Right? So let me show my last example in the next few slides is going to be a battery cycling experiment within an SEM. And in order to perform this in situ charge-discharge experiment, we designed a very unique pressure stack holder. And this was designed specifically for a solid state lithium-ion battery, where we're looking at the silicon negative electrodes specifically. They have very high expansion rates, and this pressure stack holder allows us to cross-section and observe the material while maintaining a confining pressure. It's fully compatible with our air isolation workflow. And so our charging and discharging is possible by transferring, once we created our sample, cross-sectioned in the cross-section polisher, we take it and transfer it to a base holder that has terminals in it. And those terminals will be connect to the SEM stage, which is in turn connected to a battery cycler. And by keeping the sample within the pressure stack holder, we maintain its integrity throughout the entire process. In this experiment, we're using NMC as a positive electrode and argodite type sulfide electrolyte. And there were a couple of different negative electrodes that are available, one with a silicon composite, the other with a silicon coating. And so we use GatherX to collect the EDS data. X-ray maps are collected during the charging and discharging. And our software not only collects EDS maps, but an image with each frame, and we have a playback analysis function so that we can view the full time domain of our experiment. So the data can be replayed after measurement, and we can even extract data from any portion of the time domain. So this is very effective in observation of systems with different temporal changes, like this charging, discharging experiment. Okay, in this video, let me get this one started for some reason. See if I can get this one to go to. There we go. So this is kind of a replay of that data. It collected, it took about 30 minutes to go from the charging state to about 10% charged. And you can see there's differences in how these particles behave. We're going to focus on the particle here on the right-hand side. And during this time, you can see from the backscatter electron image, it changing kind of in contrast. It gets a little bit darker. And we have an overlay of the lithium K and silicon maps on this image. And we can observe, in particular, this particle that's highlighted on the right, that the lithium is intercalating gradually into the silicon particle. This one is more, if we near the interface or closer to the interface with the electrolyte. So maybe that contact allows it for a quicker intercalation or with the lithium into the negative electrode. Next, I want to focus on these silicon particles on the left-hand side that didn't have much change. And we're going to do some further experiments in this charging and discharging cycle. So we're going to basically charge it further and not only look at what the ES data looks like, but also target it for this soft X-ray emission spectrometer to see if we can get some insights on the chemical state. What we did, this is the top image is at 0 charge. This is what the spectrum here is from the soft X-ray emission. This is the X-ray intensity maps and the backscatter electron image. Right? So at 10% charge, we're seeing a tiny little peak of the lithium there. So we're starting to see, and we're analyzing in this region right here, we're starting to see a little bit of that lithium peak and maybe some slight changes in that silicon peak shape as well. When we move to 20% charge, that peak intensity of the lithium is increasing. So we're seeing a little bit more of the lithium intercalating into that silicon particle. And we're seeing some more subtle changes in the lithium L peak shape. And again, that's corroborated, which is nice, with our X-ray data and our backscatter electron image. At 40% charge, we see more dramatic increase in the lithium concentration. We also see a little bit of a shift in the lithium peak position, indicating that we might be alloying with a silicon particle. Again, the backscatter and the EDS maps are corroborating that data. And finally, I just want to show an example of the fully discharged system. And here the peak shape has changed fairly dramatically, and the lithium intensity has increased. It's still there. We still see lithium, a little bit of lithium left in the particle. It hasn't all gone away. But this peak shape has changed. It kind of looks more like the spectrum of amorphous silicon versus crystalline silicon. So that was a very quick overview. I showed some examples from the macro to the nanoscale and different ideas. I hope I inspired you to see how you might use SEM in your own experiments. Introduced our cross-section polisher, air isolation workflows, 2 detectors that we might use in battery analysis, and showed you that quick case study. And before I open myself up to any questions, I just want to thank the Volta Foundation for allowing me to speak today. I wanted to also thank Professor Matsuda at Toyohashi University of Technology for supplying us with some of the samples that we used in these examples. And I have to very much give thanks to my colleagues, both in Japan and in the USA, who did most of the hard work in creating a lot of this data for us. So with that, on behalf of Joel and the Volta Foundation, I want to thank you. And I'm very happy to answer any questions that you might have.